Hello viewers, welcome back to class. I'm super excited to welcome you guys back to class again. You are welcome to Master Builders Online Academy. So if you are new in this channel, do consider subscribing to our channel and ensure that you turn on the post notification bell for more exciting videos. Now don't forget our policy. Anytime you are set to watch and to learn new concepts from this platform, do not welcome any form of distraction. And ensure that you do not skip any part of this video. This is for your own advantage, so that you will not skip a very vital step that would have helped you gain mastery over this lesson. Now also, if there be any part in this video you do not understand, when you watch it for the very first time, you have the opportunity to replay the video over and over again until you understand it. But if after watching it over and over again, you still have questions to ask, guys, don't hesitate. Just slide down to the comment section and make your question known to us. We will give you a benefiting answer. Now, if this is taken, let's get to work. On the board, we are asked to draw the shear force and bending moment diagrams of the loaded beam below. And now we already have the beam as shown. All we need to do is to identify the type of beam. So your analysis of bending moment and shear force comes from identifying, that's the first step, identify the type of beam. Now guys, what type of beam is this? I'll give you a second to think about that. Now, this is what we call simply supported beam. A beam that is supported at one end with a pin and at the other end with a roller. This is the first thing. Now, the second thing is identify the type of load that we have on this beam. Now, when we look at this, we have a combination of load. We have concentrated load, which are equally called point load, and we have uniformly distributed load. Also, we have how many span? 1, 2, 3. Okay, we have this point as C, then D. So we have 4 points in this system. Now that we have successfully identified the type of beam and the type of loading in this system, what is the next thing that we are going to do? The next thing we will quickly do is to draw the free body diagram. Now, the free body diagram of this system would have given us, I have a reaction at A, then I have reaction at A. This is the horizontal reaction, while this is the reaction at A, the vertical reaction. Then the other end is D, and then I call this reaction at D. Now that we have a roller here, roller can only resist vertical reaction. That's why we have only one reaction here. But for P, P resists both vertical and horizontal. And of course, we know that this horizontal reaction has no effect since this system is not loaded horizontally, or there is no inclined load. Therefore, the horizontal reaction at A has no effect on this structure. Therefore, arrow H or H arrow is equal to 0. Now, if this is taken, then the next thing we are quickly going to do is for us to obtain this support reaction on this system, the reactions that are resisting or opposing this load. And how do we obtain these reactions? We will quickly make use of what? The equations of static equilibrium, which will enable us to obtain the reactions, and also we use sum of Fx, sum of Fy, and sum of moment. These are the equations of static equilibrium as been taught. Now, all the way to the first thing we do is to use the sum of upward forces. Upward forces is equal to sum of downward forces. And now the upward forces here are the reactions. They are the ones that are heading upward. So arrow A is an upward force, and arrow B, arrow D is equally an upward force. Then reaction at B, the load at B is acting downward, the load at C is acting downward, and even the UDL is acting downward. So the load at C, at B is 10, plus the load in between B and C, which is the uniformly distributed load, we will convert it to a point load. And how do we convert this load to a point load? We will multiply this load by the span it covers. Now, if from here to here is 2 meters and from here to here is 2 meters and the entire span is 8 meters. When I add 2 meters to 2 meters, I will have 4, and I remove 4 from 8. Whatever I have here will equally be 4. That means between span B and C, we have 4 meters. So we are going to multiply 12 by 4. Then we have 12 multiplied by 4. This is the equivalent point load that corresponds to this UDL. Then finally, we have the load at C is 10 kilonewton. Then we have arrow A plus arrow D is equal to 10 multiplied by 48 plus 10. And finally, we have arrow A plus arrow B is equal to, when we add 10 to this, we have 58, then this gives us 68. This is equation 1. Now, the next thing we are quickly going to do is to obtain reaction at A and reaction at D. And of course, we know that it is impossible for us to obtain two unknowns from one equation. And what do we do now to be able to find either reaction at A or reaction at D? Like I said in our previous lesson, all you need to do is to assume a point where you will take a moment. So I can assume that I want to take moment at A or I want to take moment at B. And if I am taking moment at A, that means I want to eliminate reaction at A so that I can find reaction at B. And if I am equally taking moment at B, that means I want to eliminate the reaction at B so that I can find the reaction at A. It's as simple as this. And like I said in our previous lesson, we will take moment at A. And any point where you take moment, all the active forces there are 0. So we will simply take moment. Sum of moment at A is equal to 0. So we can simply say take clockwise moment as positive. Now, if we take moment at A, we understand that the next thing we are quickly going to do is to identify the clockwise and the anti-clockwise moment. Because we said that the sum of clockwise moment is equal to the sum of anti-clockwise moments. So, what are the clockwise moments here and what are the anti-clockwise moments? Now, let's get to work. Like I explained in the previous lesson, it is easy for you to get the clockwise moment and it is easy for you to get the anti-clockwise moment anytime you are taking moment at the left end of the system. If you are taking moment at A, just as we have now, all the loads will constitute what? Clockwise moment. When you take moment at the left end, all the loadings must constitute clockwise moment. While the reaction will now constitute anti-clockwise moment. Therefore, I will have, what is the distance of arrow D from A? It's a distance of what? 8 meters. So I will have 8 arrow D multiplied by 8, and this is the only anti-clockwise reaction moment that we have. Only anti-clockwise moment that we have. Now this one will move in this direction, this other UDL will move in this direction, and this guy will move in this direction. All the load in C now, they are anti-clockwise. So the first load that I have is 10 kilonewton from A. What is the distance of 10 kilonewton from A? 2 meters. So this is equal to 10 multiplied by 2. Then the next load is what? The UDL, which is in between B and C. So when you are dealing with UDL, first thing you do is to convert to a point load. And to convert this 12 kilonewton per meter to point load, we will multiply 12 by 4. We will have 12 multiplied by 4. Then what is the distance? At what distance is this load from A? Now that we converted to a point load, it will now be acting at the center of BC. Now from here to this point is 2 meters, and from here to here is 2 meters. That means from A to this point where the load is now acting is 4 meters. Then we have multiplied by 4. Then plus the last load is at C. What is the distance of this 10 kilonewton from A? We will have that to be 6. From here to here is 2 meters, and from here to here is 4 meters. 2 plus 4 is 6. So the distance of this load at C from A is 6 meters. Then we have 10 multiplied by 6. This is it. Then when we multiply 8 by arrow D, we have 8 arrow D. 10 multiplied by 2, we have 20. Plus 12 multiplied by this guy, we have 48. And 48 multiplied by 4, we have 32. Put that 2. Then multiply this guy by this guy, we have 16. And 16 plus 3, that would have given us what? 19. Then we have 192. Then 6 multiplied by 10, that would have given us 6. And when we sum up this result, this guy plus this guy would have given us 8. And this will give us 0, 7, 2. Then this will give us 272. This will have given us 272. Now to get ROD, we will divide 272 by 8. And ROD would have given us 8 will give us 34 kilonewton. This is the reaction at D. Now for the reaction at A, we will make use of equation 1. Now that we already know D, it's just to make ROA the study of formula. Then we have ROA is equal to 68. When we take ROD from left to right, it becomes negative ROD. Then we have 68 minus 34. And 68 minus 34 will give us 34 kilonewton. Now, why is the reaction at A and reaction at D the same? This is one of the things I explained in the previous lesson. Now, when you have a system that is symmetrically loaded, the reaction at both ends are the same. Let me do this analysis. This is the structure we are given, all right? Now, B is at a distance of 2 meters from A, and the load there is 10 kilonewton. Now, this is reaction D. C is at a distance of 2 meters from C, and the load there is 10 kilonewton. That means we have 10 kilonewton acting at equal distance from both ends, already symmetric. Now, this load here is a UDL. When we convert it to a point load, it will now be acting at the center. That means this load is at a distance of 2 meters from this end. This one is 2 meters from this end. And when I convert this load to a point load, which would have given us 48 kilonewton in each point load, from here to here would have been what? 4, and from here to here is equally 4. So it shows that all the loadings that we have here, they are symmetrical to both ends. And anytime a system is symmetrically loaded, reaction at both ends are the same. That's it. Now, if we have obtained the support reaction, the next thing we do to be able to draw our shear force diagram is to obtain the internal forces. And these internal forces are forces that we obtain at points where loads or reactions are effective. Now, at this point, I have point A, there will be shear force there. I have point B, there will be shear force there. I have point C, there will be shear force there, and I have point D, there will be shear force there. So, what is the shear force at A? What is the shear force at B? What is the shear force at C? And what is the shear force at D? This is what will enable us to draw the shear force diagram. Now, let's obtain the shear force value. Shear force values. Now, shear force at A. Now, we start our analysis from A. The shear force at A, being the starting point, is equivalent to the reaction at A. This should be noted. The shear force, now I am starting from A. The shear force at A is equal to the reaction at A. And what's the reaction at A? I can just put it this way, reaction at A, and reaction at A is 34. That is the shear force at A. Now, what is the shear force at the next point? We start our analysis from the left to the right. So at B now, before I will get the shear force at B, I will first of all pull down the reaction I had before, which is the previous shear force. And what's the previous shear force? 34. Now, when I get to point B, I have a point load that is acting downward, which is acting towards the negative direction. And I will take this load as what? Negative. I will remove 10 from this load, and this will have given us 24 kilonewton. Now, between B and C, we have internal loadings, which is what? A uniformly distributed load. That is to say, we will have two active shear force at C. So first we have shear force at C prime. This is due to the uniformly distributed load. Now, what is the existing shear force? 24. Pull down 24. Now, every other load that you have there must be taken away from the current load. Now, this load in between BC is 12 UDL. And what is the span it covers? 4. So I will multiply 12 by 4. And when we multiply 12 by 4, what will be the load? We have 12 multiplied by 4 will give us 48. When I remove 48 from this guy, what do we have? We will equally have this as negative 24 kilonewton. Now, we will now come to point C proper because there is a load still acting at point C. Therefore, we have shear force at C. This is without prime. This would have given us existing load is what? Minus 24. Now, what is the reaction at C? The load at C is 10, and it's acting downward, we are going to take it as negative. Then this will give us minus 10, and this will give us negative 34 kilonewton. Then finally, the shear force at BD is equal to, put down the previous load, which is negative 34. Now at D, the reaction there is acting upward. That means it's positive. Every upward forces are taken as positive. So I will add the reaction. And what is ROB? ROB is 34. And this will give us 0.0 kilonewton. This is when you know that you are correct. If this last reaction is not 0, you are wrong, because the loop is expected to close. Previous minus current. Previous minus current. Previous minus current. That is how you get it. Except you have a reaction. That's what you take as positive. So we took reaction A as positive because it's going up. We took reaction D as positive. Then all the loadings, we took them as negative. These are the shear force values that you will use to draw the shear force diagram. Now let's quickly get the bending moment values. Now we have bending moment values. What is the bending moment at A? Bending moment at B? Bending moment at C? Bending moment at D? Now earlier on when we started this analysis, I said that the first thing we do is to identify the type of beam. Now let me tell you the usefulness of identifying the type of beam. We know that for every simply supported beam, the moment at both ends are 0. You see why it's good that you are identifying the structure. So you don't need to kill yourself. That is to say, if this beam is a simply supported beam, moment at A is 0 without calculation. And moment at D is equal to 0. Because for every simply supported beam, there is no bending moment at the support. Now I am done with this. Now to get the bending moment at B, what do? All I simply need to do is to what? Take a section. This is A, point A, and this is point B. With a load 10 kilonewton. I will ignore every other part. I will only consider from A to B, and this is 2 meters. Reaction here is 34 kilonewton. If I am taking moment at B, like I have stated here, and that is to say this reaction at B is 0. There will not be load there because any point where you are taking moment, the load or the reaction there is 0. So the only active force here is this reaction. And what's the distance of 34 from this point B? Is 2 meters. So that means the moment at B would have given us 34 multiplied by what? 2. And this will have given us 68 kilonewton meter. Then, for moment at C, we can still decide to take moment from end A. But when we take moment from A now, we have multiple forces acting. Now, whether you take moment from left or from right, you will have equal results. So always go with the easiest one. Now, if I take moment at C and I consider it from A, I will have this reaction, I will have this, and I will have this load. That means I will have 3. But if I consider it from C, from D, I will have only 1 reaction. So I would prefer to take it from this end that will give me less stress. Then I will take moment at C from B. So this is C. And I have a load here, which is 10 kilonewton. And this is still 34 kilonewton meter. And at this point, I have D. So if I am checking moment here now, reaction here is 0. And what is the distance of this load or this reaction from this point? We said it's 2 meters, just as we have it here. And this guy multiplied by 2 will equally give us 68. Now listen carefully. Since the structure is symmetrically loaded, it shows that if reaction here is the same with this, moment here must be the same with this. As simple as that. Once the reaction at this end is equal to the reaction at this end, moment at this end will equally be the same with this, and moment at this end will equally be moment at this end. So moment at A and D are 0. If I obtain the moment at B, I have already obtained the moment at C, since the system is symmetrically loaded. So this will have given us also as 34 multiplied by 2, and this will give us 68 kilonewton meter. Now, what is the maximum bending moment on this system? This is a beam that have a span. The moment we have here will be different from the moment we have at 3 meters from A. at 4 meters from A, at 5 meters from A, similarly from this other end, what will be the maximum bending moment? That's the next thing we are quickly going to do. So to obtain the maximum bending moment, we understand that since this system is symmetrically loaded, the maximum bending moment will occur at the midspan. So at the midspan, all I need to do is to draw a beam this way. This is my reaction at A, which is 34 kilonewton. Now, this is point B, which is 10 kilonewton at a distance of 2 meters, where this is A, and then this is the midspan. I have a UDL, and the load is 12 kilonewton per meter. Now, from this end to this end is 2 meters, because we have already assumed that since this system is symmetrically loaded, the load is acting at the midspan. It's as simple as that. Now, to get my maximum bending moment, I will take moment at this point. Let's assume we call this point E. Okay? If I am taking moment at this point, what must I do? I will convert this load to point load. It will now be acting as somewhere here, and this will give us 12 multiplied by 2 as a point load. Now, from here to this point now will be 1 meter. From here to this point will be 1 meter. So if I am taking moment at this point, listen carefully, what I will have, I'm going to have 34. This will be clockwise. And we said all clockwise moments are positive. Then this guy will be anti-clockwise. This other guy will be anti-clockwise. So to get the maximum bending moment, I will have 34 multiplied by the distance of 34 from this end is 4. From this end to E is 4. This is 2 meters to C. And from C to the center is 2. Then we have 4. Then minus, understand that this is the only clockwise. Every other one will be anti-clockwise. So this 10 multiplied by 2, because the distance of 10 from E, which is the middle point, is 2. So we have 10 multiplied by 2. Then minus, now this load is 12 multiplied by 2, which will give us 24. And what's the distance of 24 from this end? 1 meter. We have 24 multiplied by 1. This is it. Now guys, when we multiply 34 by 4, what is the outcome? These are very simple. So this one are giving us 6. This guy multiplied by this guy is 12 plus 1, that's 136. This guy multiplied by this guy is 16. Carry 1. This guy multiplied by this guy is 12. That's all we have. Then minus 20 minus 24. Now this has 92 kilonewton. So for this system now, the maximum bending moment for this structure is 92 kilonewton meters. Now I have obtained the internal bending moment. I can now draw my shear force and bending moment diagram. And I said before now, to draw shear force and bending moment diagram, you will always come back to the given structure. So now let's go back to the given structure. Now bending moment diagram. All that you need to do is to identify the points that we have here. Now, at this point, I have point A. Just trace out an unseen line. At this point, I have point B. Trace out an unseen line parallel to the load, which is showing the line of action of this load. Then for this, at the middle span, we have a line of action, very faint. While at C, we equally have a line of action. Then at D, we have a line of action. Now, this is the first thing you do. Then the next thing you do is to sketch the beam. Now, what is the beam? This is the beam. I will just use a line to represent my beam from the left end to the right end. This point is A, B, E, C, D, based on our notation. Now, what is the shear force? Listen, at this point now we are plotting graph. This point is 0.0 on the line. This point is 0.0. So above the line is positive for shear force, beneath the line is negative. So now, all positive shear force will be on top of this line, and all negative shear force will be beneath this line. Now, reaction at A is 34, which is positive, and this should be done by scale. But let me assume that this point is my 34. This point is 34. So I put this as 34 kilonewton. I am done plotting for reaction at A. Now, shear force at B is 24. So I'll come to B. If from here to here is 34, that means from here to somewhere here would have been my 24. So I put down 24 kilonewton. Then when I come to what? Point C. Now Now listen carefully, something happened at point C. When I come to point C, when we come to point C, we have two shear forces at point C. The first value is negative 24. So put down the negative 24. What is the negative 24? That's what we have here. Yeah, negative 24. So from here to here is 24, then from here to here is 24. Alright? Then at C also we have a shear force of negative 34. Shear force of negative 34. And what do we do here? We'll just take this down a bit. This is 34. If this is 24, just add 10 to this, and this will have given us 34. So this is 24. This is 34. This is 0, negative 24, negative 34. Then at point B, we have 0. Shear force at D is 0. So all we need to do now is to join this point. So from here, this is the starting point. I will close this line. Between B and A, there is no load, so I will maintain a horizontal line. Then a force of 10 Newton push it down to this point. Now between B and C, I have a UDL, and for UDL you use a slanting line to join the points. So you don't need to kill yourself. All I need to do, since I have UDL between point B and C, I will use a slanting line to connect the first two moments. So between this guy and this guy, this is what I have. Anytime you have a UDL, you use a slanting line to connect the 2 points. Now from here we said a force of 10 Newton push it down to this point. Now between C and D there is no load, so you maintain a horizontal line. Then this point is 0, close it back. What you have on top of this system must be same with what you have beneath, since we assume or we have already identified that this system is symmetrically loaded. So the shear force diagram you have on top must be equivalent to the one you have beneath. Otherwise, you will have it very, very wrongly. So now the one on top is positive, so you can have this sketch. Then the one beneath is negative. You have this. Alright, this is our shear force diagram. Point A, point B, point E, point C, and point D. With respect to what we have here. Finally, we want to draw the bending moment diagram. First is to draw the beam with a line. So this is the beam. Point A, point B, point E, point C, point D. What is the bending moment? We are still using our values. Bending moment at A is 0. Bending moment at D is 0. We are plotting. And now understand that for bending moment on top is negative, beneath is positive. Bending moment and shear force are always opposite each other in terms of sign. So for shear force on top is positive, but for bending moment on top is negative, while beneath is positive. So therefore, and all the moments that we have there, they are all positive moments. So the moment at B is 68 to scale. This is 68. 68 kilonewton meter. Then at C, we have equal moments, which is also 68. So you can trace it out. This is 68 kilonewton meter. Then at the midspan, which is E, we have 92. So somewhere here we can identify this point to be 92 kilonewton meter. Now that we have plotted this point, all we need to do is to join these points together and understand that when you have point load, you use straight line, or when you have UDL, you use a curve for bending moment. So at this point, now to connect this to this point, I have point load. I will use a straight line. But between C, B, and C, I have a UDL. I will use a curve to join this point. Now between C and D, I have point load. Then I will use a straight line. Everything here is positive. This is the bending moment diagram for this system. So guys, all that you need to do is to understand principles. When you understand principles, you become a principal. And when you understand boundary conditions, you will not overstep your boundaries. So at this point, you need to understand that in system analysis, You must identify the system to know what type of structure is this. Is it a cantilever? Is it a continuous beam? Is it a simply supported beam? Or whatever type of beam. If it is a simply supported beam, understand that both ends have moment as seen. And when the system is symmetrically loaded, the reaction at both ends is the same. So guys, if at this point you have not subscribed to this YouTube channel, guys, consider subscribing to our channel and ensure that you turn on the post notification bell for more exciting videos like this. We love you guys. Thank you for watching. You can check the description below where you will find the link to the next lesson. See you guys in the